Hello, am I clearly audible? Anyone in the meeting is?
Yes.
Okay. Okay.
So I will start now. Good afternoon, everyone. Welcome to the second day of the 26th Annual Popli Memorial Lecture Series. I would like to welcome our honored guest speaker, Professor Spenta Wadia, friends and family of Dr. Popli, and the students and faculty in college today. Professor Wadia will be giving the second lecture today on the topic, A Tour of Space-Time Physics, Newton, Einstein, Hawking, and Beyond. As before, please stay muted during the duration of the talk, keep your mask on, and write your questions in the chat box or the sheet provided, and they'll be asked later by the MCs during the Q&A session. Now, without any further delay, I would like to invite Professor Spenta Wadia to take over.
Thank you so much. I'll just...
Sir, I'll stop presenting. You can start.
Yeah. Entire screen, right?
Yes, yes, sir.
Okay.
So I think you press play from start.
Sorry?
Slideshow thing, like you have to start the slideshow. It's not on full screen right now.
It's not on full screen.
So otherwise you can, if right now you want to do presenter view, you can. Otherwise right now you can do play from start. Not or play from current slide, not start.
Ah, that's right. Okay.
Yes.
Got it? Very good.
Yes.
Are we good?
Yes, sir, it's perfect. Thank you.
Okay. So, in last lecture, I had actually discussed with you, a framework for classical physics, which begins with Galileo, Newton, takes us to Maxwell's theory of electromagnetism, and we discussed after that the theory of special relativity, which is a new framework for space-time physics that was discovered, or in some sense initiated by Albert Einstein, based on works of Lorentz, Poincaré, and others. And after that, we discussed the general theory of relativity with some pictorial way of looking at theory of gravitation. And I also presented to you some experimental tests of general relativity, early tests, and also it is all the time, every experiment actually that happens in the domain of cosmology and astrophysics is all continuously testing general relativity and looking for places where it might fail in what is called a very strong field limit, like the merger of two black holes, etc. But up till now, all's well with Einstein's theory. That's what I would like to say. Okay, so we have a new framework since the early 20th century to discuss various gravitational phenomena, and I just list some of them. So Einstein's equations actually have several solutions, okay? And the first one was the solution which is called the Schwarzschild black hole, which is listed as number 3 over here. And it was discovered in 1916, just a year after, less than a year after Einstein's equations were stated in the Berlin Academy. And Einstein did not believe in this solution. He was very worried about the singularity at the horizon. And rightly so, because it took many, many years for us to understand that the singularity at the horizon, which I will mention, I'm just a bit ahead of myself. The singularity at the horizon of the black hole, which is a certain surface in the solution, is curable, actually. The other solution Einstein actually came up with was gravitational waves. He did some perturbative calculation in his theory and said that there are gravitational waves actually in 1916, but he didn't believe in them either because he felt that they are too weak to be observed. He was right. It took 100 years to observe them. And the other one is the solution for the expanding universe, actually, which is the Friedman, what is called the Friedman-Robertson-Walker universe, in which the Einstein equation has to be augmented by a term which is called the cosmological constant. Just in the equation, you add a term which is lambda times g mu nu itself, the metric. And there's a new solution, actually, which describes an expanding universe. Okay. And even that Einstein did not believe. In fact, he wrote, I do remember him writing a letter to Friedman saying that your mathematics may be correct, to Friedman or Lemaitre, one of the two. Mathematics may be correct, but not the physics, or something like that. So he was skeptical about all the most important consequences of his own equations. Very interesting, I thought, historically. Okay, so anyway, we have a framework to discuss cosmology, gravitational waves, and black holes. And then by now, all these applications of Einstein's equations and theory are experimentally very well confirmed. All right, so here, today's lecture is a little bit, what shall I say? It's a complex journey because, we cannot really go into details of everything. Because to be honest with you, I'm not an expert in everything I'm going to say, okay, also. So here it is, it's the whole universe. How can anybody claim to be an expert on everything that is in this picture? Anyway, what I'd like to just tell you that the framework of Einstein's theory and the Friedman-Robertson-Walker solution actually enables us to, understand the universe in terms of a very simple cartoon like this. And let me just tell you a little bit about the salient features. Okay, so you will see that in the left side there is a very bright spot, right? So that white stuff is something we don't know anything about. We don't understand the tip. And that is where quantum gravity, fluctuations, and string theory, and all those ideas are supposed to tell us, supposed to tell us a language in terms of which we can discuss the initial conditions of a universe in which most likely space and time as we know it today may not exist actually. So it's a extremely difficult, it's not only a technical problem, it's a conceptual problem about perhaps a new framework. And this is the new framework which people in string theory have been struggling with for the last 50 years, something like that. There is progress, but we haven't reached there. Okay, so that's the what is called a Big Bang singularity. We don't know what came before, nothing we don't actually. And if you take the three fundamental constants like Planck's constant, Newton's coupling, and the speed of light, you can make something which has the dimensions of time, okay? And if you compute that, it turns out to be 10 to the minus 44 seconds. It's an incredibly small number. And that's what is called the Planck time. And around the Planck time, we do not know what the classical theory does for sure. And we don't have a very adequately good quantum theory to describe that. 10 to the minus 44 is too small. But within 10 to the minus 29 seconds, after this so-called Big Bang, after the beginning, if it is, the universe inflates to 10 to the 30 times its own size. This is the inflationary scenario, okay? Just blows up, okay? 10 to the 30 times its size, and that's all within 100 seconds. After that, matter starts forming, and the temperature of the universe is approximately 1 billion degrees. Okay, so, all right, very hot. But approximately a month later, the temperature drops to 10 billion degrees Kelvin. So as you see, the temperature will continuously keep on dropping till it's so cold that it can support intelligent life and complex systems. Right? There is no complex system at that temperature for sure. Okay, so that these are a few facts about the early universe. And then the cosmic microwave background spectrum starts forming. I'll tell you what it is a little bit more later on. Approximately 380,000 or 400,000 years after the Big Bang. And there is a surface of last scattering, actually, which I will also explain. And that surface at that time, that is around 400,000 years after the Big Bang, was approximately 3,000 degrees Kelvin. So, it's like half the temperature of the surface of the sun, which is approximately 6,000 degrees Kelvin. Okay. And the ultraviolet light, actually, that was all the time present there. As the universe expanded, this hot object actually cooled down. And what was light of very short wavelengths stretched to wavelengths which are today observable as the cosmic microwave background radiation, which is very cold. It's at a temperature of 2.72 degrees Kelvin. So these are a few facts which I thought I'd mention to you. I think it's very important to know what's happening really in experiments and in the world around, rather than just keep on doing theory. Maybe Einstein would also agree with this, actually, even though he invented this theory without the help of experiments. But he's very singular in that sense. Okay, so this is about the standard model of cosmology. So as the universe starts cooling, there is an era in which there is utter darkness because there are no charged particles, there are only photons. But then gravity starts clumping things together, and there's a period of ionization and formation of the stars and galaxies, and it continues all the way till today, approximately 13.5 or 6 billion years. So you see where we all come from. I think it's a very humbling thing, this picture. Yeah, okay, so let me go ahead. Now, the next slide is something also which is very important for you to know about what is the energy budget of the universe as we know it today experimentally. Okay, this is slightly modified by Planck and all that, but 2015 is quite okay. 2015, sorry. So the matter that makes us up and the world around us and the one we sort of collide in our accelerators is atomic matter, baryonic matter, which the budget is just 5% approximately. Okay. Then there is, neutrinos, photons, black holes. About these black holes, I'm not so sure, but let's take this. David Spergel is a very distinguished cosmologist, so let's take his numbers. But you see that 25% is dark matter, matter which we have not identified on Earth today, but we know it exists from its gravitational effects. And there is this even more mysterious thing called the dark energy, which is parametrized by the cosmological constant in Einstein's equations and which is responsible for the accelerating expansion of the universe. So I just wanted to also flash this very important slide for perspective in front of you. Okay. Now, this is let's go back to this thing I told you. This you see this blue afterglow. What is called the surface of last scattering. Now, why is it called the surface of last scattering? Is the following: that before that epoch, matter was in a sort of a state of a plasma. Plasma means it screens electromagnetic radiation. Okay? And therefore, you cannot see anything before the scattering, the surface of last scattering. Just not possible actually, because no photons come out from there. They were all screened out. And it's only the relics of what was happening at that time that is left behind is what you see in front of you. It is a picture of the infant universe revealed in microwaves. And there's a direct link between this picture and the quantum behavior of the early universe. So I will explain that a little bit. But let us try to understand what this picture is. So this is actually a real picture. Taken by these satellites like Planck and Covey and WMAP. Now, we say that the mean temperature of the cosmic microwave background radiation is 2.71 degrees Kelvin. That's true. But there are fluctuations actually. There are fluctuations in the temperature in this picture. And they are given by these dark blue and dark red spots. Okay, so there are temperature fluctuations. And this is all experimentally measured to be between something like minus 200 to plus 200 microkelvins. Okay, micro is 10 to the minus 6. Okay, so what is the importance of this? The importance of this is the fact that temperature fluctuations reflect density fluctuations of the matter. Okay? And it is these density fluctuations. Suppose you have a spot of high density. It will become bigger, right? Because it's gravity that always attracts. And therefore, this picture actually, which is amplified over here, gives rise to what you see today. This is a picture of Hubble Ultra Deep Field Telescope. It's a view of 10 to the 11, some part 10,000 or something, part of the 10 to the 11 galaxies in the observable universe. And this is what came out of those spots, those fluctuations. The seeds of the observed galaxies are the tiny density fluctuations at the surface of last scattering, which are in turn imprinted by fluctuations of quantum gravity during inflation. Now, I was just wondering how to explain that. All right, let's go back. I'll just shake my hands a little bit. So, okay, so you see this surface over here? You can see my cursor. Sorry. Excuse me.
Yes, so now the standard model of cosmology slide is visible.
Yes, this bluish green part, that's the surface of last scattering. You see, the point is that what causes the density fluctuations? We measure temperature fluctuations, but they imply density fluctuations of matter. But what caused those fluctuations? And I think the hypothesis is that these fluctuations are essentially caused by fluctuations of quantum gravity right in the beginning of the universe, which just zipped through, because gravity cannot be screened, you see. If you have electromagnetic waves, they can be screened. You can get rid of them by putting some conductor wall, or if there is a plasma, electromagnetic wave will not propagate, but gravity will propagate. So these are the primordial gravitational fluctuations which are supposed, there's an hypothesis, I think it's a very reasonable hypothesis, to cause these fluctuations. And therefore, I just wanted to underline, it is imperative for us to understand the quantum theory of gravity. This is one argument for it. I will give other arguments later in terms of black holes, but this is actually extremely fundamental reason why we need a good quantum theory of gravity to understand these fluctuations, which gave rise to our universe of stars and galaxies and all that stuff. Okay. So quantum gravity is very important, actually. It's just not somebody's wishful thinking that, oh, well, why quantize gravity? Because you don't see it around, etc., etc. But if you want to understand the origin of the universe or the origin of matter in the universe, the way we know it today, I think it is very important to understand quantum gravity. Okay, let me move on. All right. So next we go to the next observable important consequence of Einstein's theory. And these are gravitational waves. As I said, they were predicted by Einstein in 1916 already, but detected in 2015. But we knew indirectly that something like gravitational waves do exist because of the observations of the famous binary pulsar experiment of Hulse and Taylor in 1974. So they saw two orbiting stars actually, okay, periodic orbit. And, it would just give a flash out. So these are these pulsars. And the orbit, in time, over many years, the orbit shrinks. And the orbit shrinks, that means it has given out gravitational radiation. It's a hypothesis, a reasonable hypothesis, which this hypothesis matched their experimental results. But of course, there is no direct observation of gravitational waves till 2015 by LIGO. And gravitational waves are very special, as I said many times, that gravity cannot be screened. You cannot hide in gravity. You can hide with respect to electromagnetism by just standing behind some charged conductor. You can't see that person or what a light source or whatever. But for gravity, you cannot do that because you can't hide. If you're even behind the sun, there is a star, you'll be able to see it because light will bend. That is what is called gravitational lensing. So you can't hide in gravity. And this is actually a very important point that people are investigating today in the formulation of the fundamental theory of quantum gravity, etc. You can't hide in gravity. That is why primordial gravitational waves, if we detect them, we will be able to understand what happened before the surface of last scattering. Okay, so that's why gravitational waves have a very special place, at least in my mind. But there are many other issues also, which about multi-messenger astronomy, which uses gravitational waves and X-rays, gamma rays, all the electromagnetic spectrum, all together to understand the universe. Okay, so now, as I said, they were discovered at LIGO in the United States by these two experiments, the Hanford and Livingston experiments of MIT and Caltech. And this is all a very well-known story. This is an interferometer of 4 kilometers length arm, and it's a technological marvel actually that you can measure a shift which is the size of a proton, so small size, you can actually measure. And that shift was caused by the gravitational wave which impinged on this apparatus on 14th of September 2015. Now, so I just have a little picture over here for you of this is a photograph. I mean, I don't have the full animation. I just didn't put it in. It's a simulation of the collision of these two black holes which collided to produce gravity waves which were detected by LIGO in 2015. So it's approximately 1.3 billion years ago. Everything is give and take. Okay, I mean, you cannot say it is 1.3 or 4, approximately 1 billion plus years ago. Two black holes, one which is approximately 36 times the size means the mass, not size, sorry, of the sun, So the sun's mass is approximately 10 to the 30 kilograms or something like that, if I remember. And so multiply that by 36. For the other one is 29. They came together, they collided. And they produced gravitational waves. I'll have a little animation after this one. They left behind a remnant black hole. So let me just show you that. So important point is a very simple calculation here that post the merger, the mass of the black hole is approximately.
I didn't get that. Could you try again?
Oh shit! I'm so sorry.
I don't know how to respond to that.
Excuse me. Okay, that was my iPad talking to me. So you see that there is a deficit of 3 solar masses between the final state and the initial 2 black holes. So these 3 solar masses worth of energy was liberated by the merger of these black holes, actually. So I just thought I'd mention this, and here is the animation which you may appreciate. So the energy released in the merger is approximately 3 solar masses. The peak emission rate in the final 20 milliseconds is approximately 10 to the 49 watts, and is 50 times greater than the combined power of light radiated by all the stars in the observed universe. So I've taken this all from the LIGO Virgo website, and it's really worth I just show it to you again. It's quite amazing, this simulation. And people have calculated all these things over many, many years. You see, there is a final black hole, approximately 62 times the mass of the sun, and the gravitational waves that went off carried an energy of 3 solar masses. Okay, this is the end of my discussion of the phenomenon within, which we can discuss within the general theory of relativity, and all these spectacular things that I showed you have actually happened and are happening, and people are finding more and more black hole mergers. I mean, it's just going on all the time, including mergers of neutron stars, which gives rise to gravitational waves, which people have detected. And it's an extraordinary story, actually, that is just going on. But now I'm going to go back to theory. Okay, so I want to discuss with you classical black holes. So as I mentioned to you, the black hole solution of general relativity was discovered by Schwarzschild in 1916. In fact, he was a soldier in the First World War. In fact, he died in that year afterwards. But he left us this incredible solution. So what is a black hole in simple terms? Firstly, I can say it's a solution of general relativity. And the solution has the following features. And the features are the following. So it is characterized by a surface. In 4 dimensions of space-time, it's a 2-dimensional surface, which is called the horizon, and which divides the space-time into 2 distinct parts. Okay. One is inside the horizon, which is what we usually call the black hole, and the other is the space outside the horizon. And in classical physics, once you enter the horizon, you cannot get out. And this is also true about light. Light entering the black hole, in fact, cannot come out. And that's the reason why John Wheeler called it a black hole. In fact, I think the name is due to Robert Dicke, but popularized by John Wheeler. The second important feature about a black hole is that there is a curvature singularity in the interior. But the Einstein equation actually fails there in the interior because the curvature blows up. And inside the horizon, the radial direction, you have a space-like radial direction, but inside the horizon, the light cones tilt, and so that direction becomes a time-like direction. I don't want to get into all the subtleties of the light cones of general relativity, but this is the broad picture, actually. And the point is that up till now, we understand by now, I think, a lot about the horizon physics. Okay, the physics of the horizon of a black hole implies black hole thermodynamics, Hawking radiation, and all that stuff. Okay, it is a singularity which we have absolutely no idea how to deal with. But we believe that if you have a good quantum theory of gravity, you may be able to resolve that singularity. For example, like string theory or something. Okay. All right, so this is about black holes. Now, this is Roger Penrose, very famous physicist, mathematical physicist, mathematician, got the Nobel Prize a couple of years ago for his extremely important discovery. So Penrose did not find a solution, you see. There are these well-known solutions of Einstein's equations. Schwarzschild is one of them. The Schwarzschild solution is characterized by one number, which is the mass of the black hole. So if you are very far from the black hole, you cannot distinguish it from another massive body. It's only when you come near the horizon that you'll be able to find that distinction, as I will show you later on. Now, there is, of course, black holes can have angular momentum, they can have electric charge, and the most general such black hole solution, in fact, it's one of the great successes of general relativity and mathematical physics, was found by Roy Kerr, that exact solution of a rotating black hole. And these black holes, which merged to give rise to gravitational waves and which we observed, all of them are essentially described by the Kerr solution. Once they settle down, not when they are interacting in a complicated way. There is no solution known. That is all done by numerical relativity, actually, which has also played a very important role in understanding the physics, the theory of the merger of black holes. Okay, it was initiated by Franz Pretorius, this numerical relativity. How to solve Einstein's equations on a computer. That's not a trivial point. Okay, that's a different story. So Penrose developed topological arguments to show that black hole formation is a very robust prediction of general theory of relativity. You don't have to look for a solution. Because, under very general, generic conditions, black holes form in nature. I'm sorry, in black holes form in general relativity, and of course also in nature right now. I think I can say that. And the horizon is a null surface, as I mentioned before, and it's characterized by a certain radius, which is called the Schwarzschild radius, or the horizon radius, or the black hole radius. And it's given by twice Newton's constant times the mass of the black hole divided by c squared. So, for example, if the mass of the black hole...
Find the mass divided by. Check it out.
Just 1 minute. Excuse me, just give me a second, please.
Yes.
Give me a second. There is some inanimate object that wants to interfere with my talk. This is my iPad. Okay. Sorry about this interruption. Okay, so I was saying that if the mass of the black hole is like that of the sun, like 10 to the 30 kilograms or something, then this RS, it turns out to be approximately 3 kilometers. So the mass of the sun is compressed in a radius of 3 kilometers. You can imagine the density of that object, actually. So just to give you some feeling for the numbers, actually. Okay, and associated with this radius horizon is a very important object actually called the area of the horizon. Of course, it is 4 pi r square in 3 plus 1 dimensional gravity, and it has that following formula. Now, this is a very important object. The fact that we can characterize the black hole not only by its mass, but by its radius and by the area. So the area depends upon the mass. And if you have a rotating black hole, that area also depends upon the angular momentum, but I have not really written that formula for you. You can find it in textbooks. Okay, so this is a brief slide on what is a black hole horizon. And if you look at the picture over there, this picture is it's from Penrose's original paper, actually, which is also when he gave the Nobel Prize lecture. This picture is there about a falling matter, collapsing star, developing a trap surface, a horizon, and this is another. There are many sort of renditions or coordinate systems in which you describe black holes, and this is what is called the Eddington-Finkelstein coordinate system. Okay, so we'll later on talk about black holes in Penrose's coordinate system a bit later. Okay, all right, here it is. So I just wanted to show you that all this talk which I'm doing is based on very sound mathematics, and this is the solution which Schwarzschild found of the Einstein equations which we discussed yesterday. So it's a metric, right? It's a metric, and it's a metric which has dt square with a minus sign here. See, it's in space-time, Minkowski space-time. So it's not the type of metrics Riemann considered, okay? It's a space-time metric with this factor of 1 minus rs. Rs is the radius of the horizon. And then there is the other term, dr square. And what is important is that the coefficient of dt square actually vanishes when rs is equal to small r, and when rs is sort of less than small r, this object is positive in the bracket. But you notice that when rs becomes greater than small r, the sign flips, and that's what I meant by saying that time looks like space and stuff like that. Just wanted to bring out some subtleties about the solution of Schwarzschild, actually. Okay, so now I just wanted to also tell you that if you change, in general relativity, you can work with many different types of coordinates, because that's what Einstein wanted. Why should I stick to one coordinate system? And there is a very useful coordinate system which was discovered by Kruskal and others, and then augmented by Penrose to give what is called as conformal diagram, or the Penrose diagram, in which the black hole is depicted by this type of picture in 2 dimensions. But you must understand that there is a symmetry, so that actually at each point on this diagram you have a sphere, actually, which I have not drawn because of this r squared d omega 2 square term in the metric on top. Okay, so this is the Penrose diagram. There's a singularity, there's a black hole interior which is the left of the horizon, and this is the picture of a collapsing star. Okay, this is just to tell you that almost a lot of things I'm talking about are based on very solid mathematics, actually. Okay, and now here is a very beautiful animation by Juan Maldacena about the flow of time near a massive object. So yesterday I mentioned to you that if you're near a massive object, time will slow down. So here it is, very far away from the star, the clock is going quite rapidly, but as you approach the star, the clock becomes slower and slower and slower. But if you go inside the star also, the clock significantly doesn't change. On the other hand, see what's happening. This is the exterior of a black hole where the clock is as usual, like far away, cannot make out whether it's a black hole or a big massive star, which has not become a black hole. As you go near the horizon, time stops, and that is the flow of time formula actually that comes from the Schwarzschild solution. That solution I showed you implies this, the time which the observer at infinity measures at the horizon of the black hole.
Sir?
Yes.
Sir? I'm sorry to disturb you. Could you just stop for about 2 minutes or so? The hybrid mode where we have the projecting going on, the internet has just dropped for a minute.
Okay. Certainly.
Yes, sir.
Certainly.
Yes, sir. So just
Okay.
I'll text you.
just a couple of minutes, sir, then we can continue.
There's no problem.
Thank you, sir.
Let me.
Okay, sir, you can continue now. The video is also back. Of the
Okay, good.
audience.
All right.
Thank you. Sorry.
No problem. Okay, so this is a very beautiful point actually, which we mentioned yesterday also, that it's so important for GPS. The fact that time slows down near massive objects. But it stops completely at the horizon of the black hole. It's a very beautiful fact. It's a direct consequence of the Schwarzschild solution. You can derive this. In fact, it's a nice homework exercise for you. Okay, good. Now, what is incredible, I've been giving lectures on black holes for 10 years. We have been making progress on theory, and every time, it's very apologetic, that, we have evidence there are black holes in the universe. Astronomers have said that, astrophysicists think so much, etc. Here you see, this is it. This is an optical image of the first supermassive black hole and its shadow in this Messier 87 galaxy in the Virgo cluster. This is from the Event Horizon Telescope collaboration. And the key point is that no light was observed coming from the line of sight. Okay. That's amazing, right? And black holes have also been indirectly observed even recently by Ghez and Genzel, who got the Nobel Prize a couple of years ago. And of course by the observations of incredibly small number. So the space-time grid is so rigid that it takes the collision of two massive black holes to shake it up, and the gravitational waves are just take up of this grid that we have observed. It's an amazing fact, I think. These numbers are so important. Okay, so this is about classical black holes, and now I think we start doing some more theoretical physics. So it's the following. I said that a black hole is characterized by a horizon, and the horizon has an area. Okay. Now, in 1971, Hawking proved mathematically using geometry and other tools that if you take any black hole, and if those two black holes merge and form another black hole plus radiation, then the area of the final black hole is greater than the sum of the areas of the initial black hole. Now, very important point is that this is very adiabatic. It's not a massive collision. Okay, so that's very important actually, that the equilibrium situation of the final black hole, the area of that horizon will always be greater than the sum of the areas of the initial two black holes. Okay, which basically means that a black hole cannot split apart. It does, you cannot go back. this process is irreversible. Now, in 1973, a student of John Wheeler, Jacob Bekenstein, came up with an extraordinarily very prescient idea. Just look at that formula actually, A12 is greater than A1 plus A2. What does it remind you of? In thermodynamics, you study that if you have two systems and you bring them slowly together, then, maintaining equilibrium, you bring them together, then the entropy of the final system, the thermodynamic entropy of the final system, I have to be very careful, thermodynamic entropy is always greater than the sum of the thermodynamic entropies of the initial two systems, right? This is what is called the second law of thermodynamics, actually, which plays such a fundamental role in everything. So you see, this is what Bekenstein realized, that he realized it as follows, that black holes have entropy. Now, what was his thought experiment? He said, take a hot object and throw it into a black hole. Okay, so you have a black hole plus some huge tank of hot water outside, and you dump it in the black hole. Classically, it's gone for you, for the outside universe. There is no bucket of hot water left. But that would violate the second law of thermodynamics, right? Immediately. Because it disappears and decreases the entropy of the universe, your observable universe. And therefore violates the second law of thermodynamics. So to save the second law, to avoid a contradiction, Bekenstein attributed a thermodynamic entropy to a black hole that is proportional to the area of the horizon, keeping in mind this famous area theorems of Hawking. Okay, fine. So this is Bekenstein's formula. The entropy of the black hole is some constant B times the area of the horizon. And B is an undetermined constant. Such a constant cannot be determined within the realms of classical physics. Some of these statements I'm making, you should think about them actually. Don't ask me to explain. Because it's a very important point that this constant cannot be determined from classical physics. In fact, the absolute value of entropy of any system cannot be determined from classical physics, even in ordinary matter and stuff like that. Okay. Now, the area theorems imply that the second law, in fact, there's a little bit more than what I said before, that what is important is that the generalized entropy, which is of the black hole plus the matter outside in the universe, that entropy satisfies the second law of thermodynamics. So this is a very important point actually. And this statement I'm making has only very recently, in the last 10 years, been actually substantiated rigorously by Aaron Wall. Okay, it's not a trivial point when I'm saying that the generalized entropy satisfies the second law of thermodynamics. Okay, so when the hot water bucket falls into the black hole, S matter decreases, but S black hole increases by more, and the second law is still valid for the thermodynamic entropy. Okay, now I think what I'm going to do is just do a couple of slides and end. I just want to give you an idea of the scales of length and therefore also time involved in the study of physics. Okay. If you look at the ruler, the largest length scale here is 10 to the 28 centimeters. This is approximately the size of the observed universe. And then at the end is 10 to the minus 32, which you mentioned. 10 to the minus 32 centimeters corresponds to 10 to the minus 44 seconds. So that's the realm we know nothing about it. Okay. So our understanding of nature in the small stops at around 10 to the minus 16 centimeters. And this we know because of the validity of our theories of elementary particles which are tested in the Large Hadron Collider at CERN, 10 to the minus 16. So this is the scale, actually, of the universe, radius of galaxy. This is the proton. So the photo of Rutherford. So just giving you some pictures about the scales of the universe. Okay. And the instruments which we use to understand these scales, actually. So in the large, we have all these telescopes, and more recently this James Webb telescope is there now. It's one of the big marvels of technology. It's in some time it will be able to send us a lot of very important data about the early universe. James Webb telescope, right? Then there is a super microscope at CERN, and that is the 10 to the minus 16 centimeters, which I was talking about. Okay, and so these are the, as you go higher and higher in energy, you discover more and more structure. So matter, molecule, atom, structure of the atom, structure of the nucleus, and you come to quarks. And we don't know anything below that at the moment. Okay, the quarks and the leptons are the most fundamental particles which we work with, and the theory, which is called the standard model of particle physics, actually is good till 10 to the minus 16 centimeters. Okay, so Einstein's theory is very good for large scales. Quantum theory of elementary particles, very good for very small scales. Okay, so I just wanted to give you some idea about scales. And let's go. Yes, this is another just a slide, just impressionistic slide about quantum mechanics. I think if you ask me what is the most important scientific revolution that ever took place, frankly, and I think it's quantum mechanics. I mean, and you'll see it, at least maybe not in my lifetime, but I think in yours, you'll see what I'm saying. Remember, so developed from early 20th century by Planck, Einstein, Bohr, Heisenberg, Schrödinger, Born, Dirac, Feynman, and many others. So it gives rise to new laws of particles, new laws for particles, especially below atomic scales. Experimentally, we know that. And it is the theory of our electronic devices, computers, lasers, superconductors, superfluids, and also quantum computing. Colliding elementary particles in the LHC in Geneva all follow the laws of quantum mechanics, as I said, till 10 to the minus 16 centimeters. So these are new laws for elementary particles. Just like, Newton gave us new laws for an elementary particle of classical physics, right? Then we took, those laws and discussed fluids and rigid bodies and everything. But everything comes from the basic law of Newton for 2 particles, 3 particles, 4 particles, etc. Okay. So before I leave you today, I want to do something. I want to explain to you in one slide what is the basic point of quantum mechanics. This is one way of formulating quantum mechanics. This is due to Richard Feynman. And let me just explain it to you. So suppose, in the beginning of our course here of 2 lectures, in last lecture, I started with saying that Newton's laws give you the motion of particles, actually. So, if you give me where to start from and where to end, I can solve those equations and get one solution, or maybe even 2 solutions, depending upon the type of manifold I work with. If you work on a sphere and apply Newton's laws, you'll find that there are 2 solutions, the short longitude and the long one, right? So unique, more or less unique solutions. You can prove all those things. Now, according to Feynman, in quantum mechanics, you don't know the trajectory. So you've got to sum over all of them. I mean, to go from A to B, there is a complex number associated with one path, another one with another path, another path, etc. A path can go to the moon and come back. It's contained here. I'm not joking. It's a sum over all possible connections between A and B. And that gives rise to a certain complex number, right? Because you're adding complex numbers. How to do that, how to make a sum and integral and all the subtleties of those type of stochastic integrals, it's just mathematics understood now. But this is the amplitude to go from A to B. It's a certain complex number. And the important point is that if you have an amplitude to go from A to B, there always exists an amplitude to go from B to A. You see, and it is just given by the complex conjugate. Okay, it's a very important point. This is the main, I'll explain to you next time why this is the fundamental reason why there is Hawking radiation. In quantum mechanics, if you fall into a black hole, something has to come out because of this equation. And this amplitude which I wrote down satisfies a Schrödinger type equation. This is called the Feynman kernel, and you can write out a differential equation by varying the coordinates at this point small a, and you get a differential equation by Schrödinger's equation. And the last point actually is the Born rule, that the probability for this process to go from A to B or B to A is just the absolute value square of this amplitude. So this is all of quantum mechanics. Actually, it's true. This is all of quantum mechanics in one slide. I mean, the principles are just these. Everything else follows from what I have said. Okay, I think that's good enough for today. And we can have some questions, if you like.
Thank you, sir.
Yeah.
Okay, so before we move on to questions by the in-house audience, people who are in the meeting, could you, if any of you have any questions, you could either unmute and ask or put them in the chat box. Okay, then I think we can start off with audience questions. So the first question, which is my question, is you talked about fluctuations in quantum gravity in the early universe, and I wanted to get an idea of what exactly you mean by fluctuations here. As in, do the forces, their magnitudes vary? What does fluctuations imply? What changes or what fluctuates?
All right. Let's put it this way. So suppose I'm running out of charge. So just give me a minute.
Yes.
Charge my computer. Yeah. So
Yes, sir.
Let us. Just take some material. Let me explain the notion of. In some material, you understand that particles may be put together or come together so that the density varies as you sort of. Traverse the volume of the object. So a good example is, let me give you an example from daily life of some material or some object in which the density varies in some obvious way. I can't think of it right away. I tell you what. Okay, this is a very mundane example. But when you make this Belpuri type of stuff, you have ice plates and you have all types of stuff, wonderful stuff. You see, if you look at a small volume here and here and here, you'll find that the density will be different actually, right?
Yes.
Okay. So this is just to explain that it's possible to imagine a system in which density varies with space. Now, it can also vary with time, right? So
Yes.
remove something here and put it here, etc., etc. So you can imagine this type of situation. So a fluctuation of density means that if you observe the density at that point at different times, for example, it will change. So that's the fluctuation.
Okay. So does that mean that the very fundamental forces, their magnitudes, or the force that acts between particles that has changed with time?
No. It just says that the density of this plasma behind the surface of large scattering, that is changing, and what is changing it is quantum fluctuations. Now, what is a quantum fluctuation? That will be the next question. That's not easy to explain. It's easy to explain in the sense that you understand temperature fluctuations, right?
Yes, sir.
Okay. Just replace temperature by Planck's constant mentally, and it's a quantum fluctuation. And for example, if you very simply way. So in quantum mechanics, as I explained to you, that the basic objects are amplitudes, and you have these probabilities associated with them. It basically means that you cannot really localize, for example, the position of a particle or know its velocity exactly.
Yes, sir.
So you write the famous uncertainty principle, delta X, delta P is greater or equal to H bar from P pi or something like that. Now,
yes,
that is, so position is therefore a fluctuating object. It doesn't take a definite value. For reasons unknown to us, in a very deep sense, position is fluctuating and momentum is fluctuating, but they satisfy a certain constraint, which is the Heisenberg uncertainty.
Yes.
Am I getting across?
Yes, sir. I think yes. Quantum fluctuations and quantum mechanics is something we studied also. So
right. So these fluctuations which you see in the surface of large scattering, in the density and the temperature, are caused by fluctuations of quantum gravity in the very early universe.
Okay, sir.
That's the best I can do at the moment.
Thank you, sir. So we have another question from the audience. Why is the radial distance of black hole time-like? Is it because we have observed that light can't come outside a black hole?
Yeah, in a sense, yes. I mean, but I gave you the mathematical reason that factor actually flips sign. But what is very important is I don't think you should take all this very seriously, because we can invent another coordinate system, like the one I showed you, the one which Pascal Penrose invented, in which nothing like this happens. But the formula for the metric is a little bit different. So you go straight inside the black hole. Nothing happens.
Okay.
That's called the freely falling observer across the black hole. There is no such flip of light cones or anything actually. The light cones will always be the way they are.
So, but the different coordinate systems should imply the same physical meaning or the same physical result, right?
Absolutely. So that's where the challenge is actually. So you say that the singularity in the Schwarzschild metric is a singularity. You must know how to remove it. And you can remove it by going to a new coordinate system. And therefore, there is really no singularity physically. But you cannot do this for the curvature singularity. In the inside the, which is sort of what shall I say, screened by the horizon of the black hole. No matter which coordinate system you are in, there is a singularity, because it's a curvature singularity.
Yes, sir.
Yes.
Okay. So we have another question. Someone has asked, what exactly does the mass of a black hole imply? As in, a black hole itself, what does the mass really mean over here?
Oh, the mass of the black hole is just something which you will measure. Like, for example, take a star, which is not a black hole, like a neutron star, for example. Far away, there is we will be able to observe its mass. Various ways of doing it. Not a black hole. Then gravity starts crushing the star, and it becomes a black hole. Once the star enters the event horizon, right, or this
Yes.
horizon that's forming. Okay, but the mass doesn't change. There's nothing to do with the mass.
So the mass is the mass of the star that formed the black hole.
Exactly. But the mass is related to the event horizon radius. That's important.
Okay, sir.
That's why I said that if you take the mass of the sun, the event horizon radius will be 3 kilometers. If you take the mass of some much 100 times more, then the radius of that object will be even bigger. That's all.
So the radius is a good way of knowing the mass of the black hole.
Exactly. Because there's a formula.
Yes.
Radius is proportional.
Okay. Yes.
Sorry.
Someone has asked, how can one distinguish between if a particle is moving away from me in a static space and the space between me and the particle is expanding while the particle is at rest in space?
Say it again. I'm sorry, I didn't follow.
Yes, sir. So the question is, how can one distinguish between whether a particle is moving away from an observer in static space or the space between the observer and the particle is expanding while the particle itself is at rest?
Can we tell if the space is expanding or if the particle is moving and it's not that the space is expanding?
Oh, I see. I'm sorry, I'm not able to connect with the question, but is it the statement that if you are, let's say, in a universe at a certain time, a universe is expanding, and there are two observers, and there's a certain space-time distance between them. Is the question that space-time distance actually changes when the universe expands?
Yes, I think they're saying that if something appears to be moving, like say I'm looking at a galaxy far, far away from the surface of the Earth and it appears to be moving away from me.
Yes.
That one is that's because of the expansion of the universe, which is often what's said, or it could have a physical velocity with respect to me. So can we distinguish by experiment which of the two it is?
Is it a meaningful question? That's what I'm worrying about. That when you talk about the recession of a galaxy in a certain geometry, the rate is what is given by the geometry. I mean, there is no notion of something else happening, right?
Yes.
Yeah, that's my sense of it. Yeah. I hope I'm clear. I mean, you couldn't connect to the question very well.
Okay, sir. Okay. So it's okay. We can move on to the next question. Okay, sir, do you think the mathematical constructions like Morris-Thorne wormholes will be a possibility? Black holes was also once a mathematical construction by Einstein initially, then observed years later.
Yeah, I mean, I think we deal with wormholes all the time these days in our subject of quantum gravity and string theory. They are there actually, but there is no. But one important point: a wormhole is like a. Yeah. Okay, let me put it this way. So Einstein's equations have solutions which are wormholes, and we know how to deal with them. But that doesn't mean actually that you can really travel from one universe to another universe or travel faster than the speed of light. All that is not allowed. By the theory, it's not allowed. It's allowed maybe in some science fiction books, but today our understanding is that that type of thing is not allowed. But we use it all the time. I'll give you an example of a wormhole. Something which is analogous to a wormhole. in quantum mechanics, you must have studied the double bell potential.
Yes.
You have a potential which has two values, right? There's a hum, all right? Now, if you are in each of these valleys, you can jiggle around and understand the wave function quite well.
Yes.
But once in a while, there is a particle that tunnels between one well to another well. So the wormhole is like that. It's a solution with imaginary time, the Euclidean theory of gravity, and we understand these things. Yeah. So now, it's not. It's not a pain, in that sense. It enables you to calculate a certain transition amplitude type of thing.
Yes, sir. So I think the question is asking whether such a mathematical structure, although well understood, could this ever be found in reality? Do we expect, and are we looking for it?
No, so that's what I'm saying. Its consequences certainly we will be able to understand.
Yes.
Its contribution to certain things that we would like to compute definitely will be there. But it cannot be that it's like something, some object which you lay your hands on. Like a black hole is like that, you see.
Yes.
That's an object, that's a thing, right?
Yes. Okay, so this in the sense is more of a process similar to quantum tunneling. It's something that could happen.
Something that connects.
Yes.
Space-times, right.
Yes, sir. Okay. So another question is about black hole entropy. What exactly happens within the black hole? Where does this increase in entropy come about when, say, a body falls in?
That is not very difficult to understand. You see, because I said that the entropy was proportional to the area, right?
Yes.
The area goes to the square of the mass, right?
Yes.
So if you throw something in, the mass will slightly change, right?
Yes.
So the entropy will slightly increase. Right?
Okay, sir. I think that's all the questions we have for today. Does anyone else in the meeting, if anyone wants to ask anything? Okay. So then I think, thank you, sir, for that very enriching lecture. And we look forward to tomorrow for the last day of the event. Thank you so much, sir.
Thanks a lot. Great. Take care. Bye.